Hey everyone, welcome back. I'm absolutely thrilled to have you here for another explainer. Today, we're picking up right where we left off in our software architecture journey for HND computing students. We're diving into part 2 of our series on structural design patterns, specifically tackling the incredibly useful facade pattern in depth, and then taking a high-speed tour through 4 other essential structural patterns, all using Python.
All right, so here's our game plan for today. We'll kick things off by looking at the sheer chaos of complex systems. Then we'll break down the facade pattern and actually code it up. After that, we'll blaze through 4 more structural patterns, compare them all side by side, and wrap up by testing your pattern knowledge. Let's get right into it.
Section 1. The chaos of complex systems. Now, what's really interesting about this setup is, well, to truly appreciate a brilliant design pattern, you kind of have to feel the pain of a bad one first, right? Imagine you're tasked with building a brand new student portal for a college. Sounds easy enough, but behind the scenes, without a facade, your poor client code has to manually and individually coordinate with a whole bunch of subsystems. We're talking the student database, the fee service, the library service, hostel service, email service, you name it. It is messy, tightly coupled spaghetti code, literally a maintenance nightmare. If even one of those underlying services changes, boom, your client code breaks. But check out the alternative with a facade. Your client talks to exactly one thing, the registration facade. That's it. It's just beautifully simplified architecture.
Section 2. The facade pattern explained.
So how exactly do we achieve that Zen-like simplicity we just talked about? Well, the facade pattern provides a single simplified interface to a complex subsystem. Instead of your client pulling its hair out trying to interact with a dozen different classes, it communicates with only one class, the facade. It completely hides all those messy implementation details and drastically reduces coupling. This makes your code infinitely easier to read and honestly so much easier to maintain. Now, a quick caveat. The facade doesn't actually replace those underlying subsystem classes. Not at all. It just acts as a really friendly coordinator for them. To put this into a real-world perspective, think of it like a college admissions office. You know, where you submit just one application instead of physically visiting 5 different departments. You hand in your paperwork once, and the admissions office, which is your real-life facade in this scenario, handles routing all your info to housing, financial aid, registration, the whole shebang.
When you map this out architecturally, the boundaries become incredibly clear. You've got your client on one side, your heavy subsystems like the student DB, fees, library, and email on the other. And sitting right there in the middle is your facade, acting as a protective shield between your client and all that heavy lifting happening in the background.
Section 3. Coding the facade. Okay, let's dive into this and move from abstract theory to some actual Python code. Because for our HND computing students, this is where the rubber really meets the road. First, let's look at the raw subsystem classes. We've got a student database with a register method, a fee service with a pay method, a library service with an activate method, and an email service with a send method. Now, without a facade, your standard client code would have to instantiate every single one of these classes and call all of these methods individually, strictly in the right order. Imagine writing that out 50 times across your application at 2 a.m. Yeah, no thank you.
So enter the registration facade class. In our init method, we instantiate all those subsystems just once. Then we create a single, super easy to call method named complete_registration. Inside this one method, we neatly package the specific execution steps. First, we register the student, then we pay the fees, then we activate the library account, and finally, we send out the welcome email. All that complexity, it's wrapped up in one tidy little package.
And here's the payoff. The final result from the client's perspective is just glorious. The client code shrinks down to just 2 simple lines. You create the registration facade object, and you call complete_registration. The output shows all 4 subsystem actions firing off and completing seamlessly. This dramatically improves readability and, honestly, absolutely proves the pattern's worth in any layered architecture.
Section 4. 4 more structural patterns.
Now, the facade is fantastic, for sure, but it's just one tool in our structural pattern toolbox. So let's keep our campus tour going and rapidly unpack 4 more structural patterns you really need to know. First up, the bridge pattern. Its core purpose is to separate an abstraction from its implementation so that the two can vary independently. And this brilliantly illustrates a solution to a very common, very frustrating coding trap.
Let me explain. Imagine you're building a learning management system, an LMS, and you need to generate different report types, like a student report or a faculty report.
But you also need different export formats, right? Like PDF or Excel. If you try to use standard inheritance here, you're going to end up with a combinatorial explosion of subclasses. You'll have student report PDF, student report Excel, faculty report PDF. You get the idea. The bridge pattern completely prevents this by keeping the report logic and the exporter logic entirely separate, allowing you to mix and match them dynamically without all that massive, messy subclassing.
Next on our list is the composite pattern. Its main job? To let you treat individual objects and groups of objects uniformly. I want you to think for a second about how you interact with tree-like hierarchical data structures.
A really perfect metaphor for this is a standard college folder structure on a computer. You might have a department folder, and inside that a single faculty object and maybe a whole students folder. Using the composite pattern, you can call an operation, let's say count_members, on a single individual faculty object, or you can call it on the entire massive department folder, and it uses the exact same logic. You don't have to write totally different code just to handle a single item versus a giant group of items. It just works.
Then we have the flyweight pattern. Now, the absolute core superpower of this pattern is extreme memory conservation in massive applications. It essentially reduces memory usage by sharing common object data. Paint this picture in your mind. You're building a heavy online exam platform that needs to display, say, 50,000 exam questions all at once. If every single one of those question objects stores its own font, theme, and layout data, your application is going to crash hard from memory exhaustion. It's just too heavy. Flyweight solves this by separating the heavy repeated formatting, the shared info, from the lightweight unique information, like the actual question text and the correct answer. It stores that heavy formatting exactly once and just shares it across all 50,000 objects. It is incredibly efficient.
And the final pattern in our rapid-fire tour is the proxy pattern. This pattern provides a placeholder or a representative object that strictly controls access to another underlying object. Think of a student results system. You obviously don't want just anyone accessing sensitive grade data directly, right? The proxy acts as a strict security guard. When a request comes in, the proxy checks the permissions before it grants any access. So students are only allowed to see their own individual results, while administrators are granted access to see everything. The proxy handles that control seamlessly behind the scenes.
Section 5. Comparing the patterns.
We have definitely covered a lot of ground really quickly here. Let's slow the pace down just for a second. If you're taking notes, you might want to screenshot this part. So the crucial point is understanding how each pattern uniquely solves a specific architectural headache in our college ecosystem. The facade? It simplifies complex interfaces, just like our admissions portal. The bridge separates abstractions from implementations, saving us from that subclass explosion in our LMS reports. The composite lets us treat individuals and groups uniformly, which is perfect for campus folders. The flyweight saves massive amounts of memory by sharing data, absolutely crucial for handling 50,000 exam questions. And finally, the proxy controls access, acting as the ultimate security guard for our results system.
Section 6. Test your pattern knowledge.
Now that you've got this powerful blueprint in your head, it's time to actively apply what you've learned. Let's turn this abstract theory into some practical engineering. Here's a scenario to chew on for your own code. Let's say you need to add strict security checks before a student is allowed to view a massive 50,000 question exam, and that exam relies heavily on shared formatting to save memory. Which two structural design patterns would you need to combine to build that system flawlessly? Think about the security guard and think about the memory saver. I'm going to leave you to debate that architectural combination as you write your next Python script. Thanks so much for joining me on this explainer, and hey, happy coding!